Hello everyone, and welcome back to SIMPLEGYAN. Have you ever wondered why the power lines outside your house carry tens of thousands of volts? But if you plugged your smartphone directly into that line, it would instantly explode? Or why we need those massive, buzzing substations in our cities just to turn a light bulb on? The answer lies in one of the most critical machines in modern history, the transformer. Without them, our entire electrical grid would collapse and long-distance power transmission would be impossible. Today, we are going deep. We are going to break down exactly how step-up and step-down transformers work, the physics of mutual induction, and the real-world engineering behind them. To understand a transformer, we have to start with the physics of electromagnetism. It starts with a simple fact. Current flowing through a conductor creates a magnetic field. But here is the catch. A steady direct current, or DC, creates a static magnetic field. It sits still. For a transformer to work, we don't want static, we want movement. We need a changing magnetic field. This is why transformers only work with alternating current, or AC. They do not work with DC batteries. When AC power flows through the first coil, which we call the primary coil, the current rises and falls. This causes the magnetic field to expand and collapse continuously. Now, imagine we place a second coil, the secondary coil, right next to this changing magnetic field. Something magical happens here. Faraday's law of induction kicks in. That changing magnetic field cuts across the wires of the secondary coil and induces a voltage inside it. This is called mutual induction. There is no physical wire connecting these two coils. They are electrically isolated, but they are magnetically coupled. So, how do we decide if the voltage goes up or down? It all comes down to the number of turns in the wire. This is called the transformation ratio. The formula is very simple. The voltage in the secondary coil divided by the voltage in the primary coil is equal to the number of turns in the secondary divided by the number of turns in the primary. In simple English, if you wrap the wire more times on the output side, you get more voltage. Let's define the two types. First, the step-up transformer. If your secondary coil has more turns of wire than your primary coil, the output voltage will be higher. We use this to boost power. Second, the step-down transformer. If the secondary coil has fewer turns than the primary, the voltage drops. We use this to lower power. But remember, you cannot create energy out of nowhere. If the voltage goes up, the current must come down. Let's look at the real world. Where do we use step-up transformers? The biggest use case is at the power station. Imagine a power plant generating electricity at 11,000 volts. If we try to send that through hundreds of miles of wire to your city, the resistance in the cables would generate massive heat. We would lose a huge chunk of that energy. To fix this, we use a massive step-up transformer right at the station. We step that 11,000 volts up to 132,000 volts, or even higher. By increasing the voltage, we drastically lower the current. Since heat loss is caused by high current, this makes the transmission very efficient. Now, let's talk about the step-down transformer. This is the hero of safety. Remember that massive voltage we sent across the country? You definitely do not want that entering your house. It would destroy your appliances and be incredibly dangerous. So, we use step-down transformers. You have seen these on telephone poles or as green boxes on the ground. They take the high voltage from the street and step it down to the standard 230 volts or 110 volts that comes into your wall sockets. Even inside your phone charger, there is a tiny step-down transformer converting that wall power down to just 5 volts for your battery. Real-world engineering is never perfect. Transformers get hot. Why? Because of iron losses inside the core. If you're an engineering student, pay attention, this is important. There are two main types of losses. First is eddy current loss. The magnetic field induces swirling currents inside the steel core itself, which creates heat. To solve this, we don't use a solid block of steel. We use laminations, thin sheets of steel insulated from each other. The second is hysteresis loss. This is caused by the friction of the magnetic domains flipping back and forth 50 or 60 times a second. To solve this, we use soft iron or silicon steel. From the massive giants keeping our national grid alive to the tiny components charging your phone, step-up and step-down transformers are the silent workhorses of our world. They allow us to manipulate electricity to suit our needs efficiently and safely. I hope that